Starcloud says an NVIDIA H100 GPU reached orbit on its Starcloud 1 satellite in November 2025. The company also says the mission later ran a version of Gemini and trained Nano GPT in space. That is an engineering demonstration, not proof that a profitable data center exists. A data center must deliver useful compute continuously, reject heat, move data, survive radiation, and refresh hardware at a competitive cost. The verdict up front is conditional. Orbital AI looks most credible first for data born in space, not as a general replacement for the cloud on Earth. Why is cold space not free cooling? NASA 2026 Thermal Control chapter says a spacecraft balances absorbed solar, reflected, and planetary heat plus internally generated heat against stored and radiated heat. Vacuum provides no surrounding air that can carry server heat away. A processor's electrical power becomes heat inside the spacecraft. First, that energy must travel through interfaces, heat pipes, or fluid loops. Only then can an external surface radiate it toward a heat sink, typically deep space. The decisive object is not the server alone. It is the entire physical path from chip to radiator. NASA identifies 4 variables behind radiator performance: usable surface area, infrared emissivity, operating temperature relative to the sink, and the view toward that sink. Orientation matters because a radiator that absorbs sunlight or sees a warm planet faces a different balance. NASA also calls power density a major challenge when electronics are stacked with no direct path to a radiator. There is no universal square meter answer for an AI payload. The area depends on heat load, temperature limits, surface properties, orbit, and geometry. But every design must publish that thermal ledger rather than treat cold space as the answer. A solar array headline is not the same as continuous power at the processors. NASA describes the electrical power system as generation, storage, conditioning, and distribution. Solar cells produce no power during eclipse periods, and their performance changes with sun angle and degrades over emission through aging, radiation, and contamination. Arrays also add mass, surface area, cost, deployment complexity, and pointing constraints. Batteries bridge darkness, while conversion, networking, thermal control, guidance, and housekeeping consume part of the supply. The useful economic number is firm delivered IT power across the full orbit, not peak array output in perfect sunlight. Launch economics begins with the complete mass and volume, not the compute box. The stack includes accelerators, memory, arrays, batteries, radiators, thermal plumbing, shielding, communication, structure, deployment mechanisms, and launch interfaces. NASA Current Integration chapter also shows that licensing, safety analysis, materials, venting, debris planning, models, and testing sit inside the delivery process. A universal launch price per kilogram would be misleading because mission, vehicle, integration, orbit, and schedule differ. The stronger test is to count every launched support system and then price replacement or servicing over the hardware's useful mission life. The network does not end at the satellite. NASA describes both space and ground segments, including terminals, tracking, routing, and operations. Laser communication can support high-capacity links, but its narrow beam demands accurate pointing. NASA says cloud moisture can attenuate optical links enough to prevent communication, forcing a later pass or a handoff to another ground station. That does not make laser links unusable. It makes availability an engineered service. There is also no universal orbital latency advantage. It depends on orbit, routing, ground coverage, and workload. Processing data already created in space avoids more of the network tax than uploading ordinary cloud traffic from Earth. Radiation changes the reliability ledger. NASA separates long-term cumulative damage from transient single-event effects that can alter logic or memory. It describes a common spacecraft approach that combines commercial components with radiation-tolerant support such as error-correcting code, watchdog timers, memory scrubbing, and redundancy. None of this proves that a commercial accelerator cannot operate in orbit. One already has in a company-reported demonstration. It does mean sustained service requires fault detection, recovery, spare capacity, shielding choices, and mission-level evidence. Those protections consume mass, power, engineering time, and sometimes performance, so benchmark speed alone is not the business case. In February 2026, the FCC Space Bureau accepted for filing and sought comment on a SpaceX application for an orbital data center system of up to 1 million non-geostationary satellites. That is a remarkable signal of commercial intent. The boundary is just as important. Acceptance for filing is not authorization, deployment, or delivered computing capacity, and up to is not a built fleet. The notice says the proposed system would use high-bandwidth optical intersatellite links. At that scale, spectrum, tracking, debris, collision risk, ground connectivity, and regulatory review are part of the infrastructure. A filing can reveal ambition. It cannot prove economics. Use 6 tests before accepting an orbital data center claim. First, ask for firm-delivered IT power across eclipse, not peak generation. Second, ask for heat load, radiator area, temperature, orientation, and thermal path. Third, count the full launched mass and volume, including deployment hardware. Fourth, define sustained network service through real ground availability, not one laboratory link record. Fifth, state mission life, fault recovery, replacement, and hardware refresh. Sixth, distinguish an application, test, contract, and operating fleet, then include licensing and debris obligations. Compare the same workload and service level with an Earth alternative. A beautiful spacecraft rendering is not yet a ledger. The early economic fit is processing data that is already created in orbit. Earth observation, astronomy, weather, or satellite operations that can reduce what must be sent down. That is a circuit and ledger inference from the physical constraints, not a confirmed market outcome. General consumer cloud work starts with more disadvantages because its data, users, grids, fiber, technicians, and rapid hardware refresh already exist on Earth. The conclusion is not that orbital computing is impossible. It is that a demonstration becomes a data center only when the whole system closes. Follow delivered watts, radiator square meters, launch kilograms, sustained bits, mission life, and permission.